received her PhD in Physics and Materials Science from City University, Hong Kong in 2017. And then she worked as a postdoctoral research fellow at Lancaster University from 2018 until 2019. She's currently a lecturer, assistant professor in the School of Electronics and Computer Science at the University of Southampton. And her research focuses on experimental quantum nanotechnology and its device applications. Her group develops a diverse range of photonic and electronic devices, including field effect transistors, solar cells, plasmonic devices, and AI quantum optical security IDs. For this talk, she will be presenting her group's work on learning and predicting the aging properties of quantum security identifier. Over to you, Nema.
Okay, thanks, Alex, and thanks for inviting me today for the webinar. So let's start I'm going to introduce my project, which is related to quantum security, and in single line, let's say, let's light be your fingerprint. So, okay. So, you know that global counterfeit caused over 1.8 trillion in economic loss due to fake identity, fake medicine, fake component, fake device, and so on. So, for example, if you look to this image, can you tell us what's real and what's fake? How it look like, even if it looks like exactly the same as real one. So I'm using nanomaterials, which is called quantum dots. This is a glow materials, and each tiny dot actually is a tenth of 1,000 times smaller than the grain of sand. And these materials emit light. And actually the beauty is the light is uniquely shaped by the dot size, dot structure, and no two dots ever behave the same. So this came up to actually how we can use this light to build a pattern, creating a pattern out of this light by then creating a complex security fingerprint that is mathematically impossible to clone. The idea here come to a system called a buff system, which is a physical unclonable function. So what is a physical unclonable function? It is a mathematical function. It is derived from the behavior of complex physical object or device. The key point of physical unclonable function is in simple way, if we have an object here, as you see on the right hand side, we would like to authorize this and make sure this is a real or fake. So we can send some challenges by the phone, and we will get a response, and then the response transmit to a server, and the server will validate the response. In single way, we can just say it is based on challenge response pair. So the buff actually could be a strong buff or weak buff, so all based on the number of a challenge response pair. In my research, I use nanomaterials as a materials used for a buff system, exactly actually optical buff. And in very simple way, we have a challenge source here. It could be a laser, it could be a light source, it could be any kind of LEDs or whatever. And then we will have optical token here, where we have a layer of nanomaterials, which is quantum dots in this case. And then from here, we will excite this quantum materials. We will get a random optical response, and we're going to image the system, process the data, and finally transfer this data to a fingerprint. And at the end, we're going to compare this with the pre-stored data. So I used to work with a spin-out company where we would like to integrate this in the market. So we actually simply printed these nanoparticles into a medicine, for example, and by using some flashlight of the phone, we can get some responses back, and then we will get all information about this product. So, for example, the date and also expiry date, the information about the company, and it give you all information about it is a real product. In general, we could use different type of materials for the security application. For example, any kind of low dimension materials or any kind of luminance materials. Here are two examples of low dimension materials. The first one is 2D materials, where you can see clearly if you have a flake of 2Ds, there is a random distribution of the emission coming from this flake, and even the flake size itself is randomly distributed onto the surface. The same for colloidal quantum dots. These are nanoparticles. When spread to any substrate, it will be randomly distributed. So for a strong buff, and again to build a large number of CRBS, we're looking to have randomness, imperfection, impossible to replicate, nonlinear optical response, because this will actually generate a large number of CRBS, and finally easy to measure and have high emission response. For 2D material, it's really hard to control because the emission coming from the 2D is very weak and is not easy to measure, especially by phone. So for that, we're going to focus more on colloidal quantum dots. Okay. So out of colloidal quantum dots are semiconductor materials, is a tiny small particles size between 2 to 10 nanometers. We used here in my research, I use copper indium sulfide, zinc sulfide quantum dots. Why is copper indium sulfide? For many reasons. So we notice that at one single excitation wavelength, we have multiple emission peaks. So this means at that just one single, let's say, challenge, we could get two responses instead of one response. So you can see clearly here, these are copper indium sulfide quantum dots, and these are a range of different excitation wavelengths starting from 250 up to 345. And each time when we excite, we completely getting a random response or different responses. So this will increase something called encoding capacity. So how much information we're going to extract from this material, and also will enhance the signal speciality. So we think about, okay, if we have two peaks out of one type of quantum dots, how about if we mix two colors of these quantum dots? So if we mix green ones and red ones. So the green ones wavelengths mean peak around 530 nanometer, the red ones is around 650. So at the interfaces of the two colors, we even can get 4 peaks emission, which means we can have 4 responses in just one single excitation. So again, this will increase the number of CRBS. And finally, why copper indium sulfide? Because nanomaterials in general are very, very sensitive to environment. Copper indium sulfide is very stable over time. So we test these materials in film over around 4 months, and actually it's kind of stable material for us to use for application. Okay, so how we transfer optical measurement to fingerprint generation. So in simple way, we start with colloidal quantum dots. We can easily make a large sheet of film from these colloidal ones, and we cut it to a small pieces, and then we can take some optical images under microscope or under spectrometer. Then we can extract some features, and then we normalize the data, and finally we digitalize the data. So instead of having this feature, we will have a number out of this feature, so 0, 1, and so on. And after we got these numbers, number of bits coming out from these features, we have to evaluate the system. So in general, these are 3 different systems we used currently. So the non-copper one, based one, when we excite with one excitation, we get just one emission peak. So this actually gives us a single spectral encoding. When we have a copper-based ones, when we excite in one single, we get 2 responses peaks where we increase the number of features, and this is called dual spectral cross encoding. And finally, when we mix these 2 different colors of copper-based ones, we have multi-signature. So at the end, the first system have limited parameters, so which is called lower encoding capacity, because the encoding capacity is actually related to the number of features we can extract. And then the second system, it's increase the features, but the last one is more better, higher features we can create, and this will make our fingerprint more complex. Finally, once we create this number of bits, we have to evaluate the system, so which is called system performance matrix, and we have to check the reliability, uniqueness, entropy, and efficiency. Reliability means the same tags under the same condition should give us always the same response. It's related to something called intra-Hamming distance. And uniqueness, each tags should produce different responses, which means inter-Hamming distance. Entropy is the number of bits unpredictable. Efficiency, how much storage data we can extract from the system. I'm not going to go in details here because I would like to have a real example and how we integrate AI to this system. So the current system limitation is we extract these features manually, so we actually lose a lot of important information through these kind of peaks. Extracting and encoding and fitting, all these is time consumable, so it takes maybe a days or maybe 3 days, 4 days. Also, security is risk with data storage because we store this data into our computer. So what's the point here? And finally, how we're going to build an edge device implementation if we can do this manually. And we have to integrate an AI-driven discovery framework where it can support us across all these limitations. So AI can support us on feature extraction, reducing time processing, improving the data, and finally build an edge device where everything will be on our phone. So how AI can implement our value, just in simple way again, we will start with quantum dots film. We're going to use any kind of excitation source, and we will build something called excitation emission map. And we're going to feed this excitation emission map to autoencoder, where we would like to train and extract the feature directly from the autoencoder by extracting the numbers. And not just this, we have model training stage, we have fingerprint enrollment stage, and also we will have verification phase. So we would like to build the verification phase inside the model as well. And finally, we will use a machine learning to also try to attack the system. So, okay, how much strong our system will be. So let's go to stage 1 and 2, where we train the model. So actually we use as I said, encoder-decoder model, where we design to learn intrinsic physical directly from the optical signature. The model have 2 phases. So first phase is feature extraction or reconstruction focus, where we learn the general structure of emission excitation map. And the second phase is manifold shaping, where we discriminate. So we're trying to actually create a different responses for different tags and then identify these. So it's based on encoder and decoder. So as I said, encoder will be mainly to extract the feature and compress these to latent space, and finally produce a binarized fingerprint. The decoder will reconstruct the EE emission map, and then we would like to keep it as much as possible similar to original optical features. So this is an example of training process from reconstruction first. So the stage 1 is the phase 1 when we reconstruct the fingerprint, and the stage 2 where we have actually different tags have different responses, or different tags have different fingerprint, let's say. So this is showing the reconstruction first. This is stage number 1, and then in stage number 2, this is showing how machine learning can actually differentiate between different tags. And each group of tags have kind of cluster where we have the same tags are very close response together. So it make a cluster compact at the same tag response. So finally, machine learning itself will help us to evaluate the system directly. So we create a Hamming distance matrix inside the machine learning. So the resulting bits will stored within the data space, and during the verification, the new emission excitation map will generate a fingerprint, and then we're going to compare the new ones with the stored ones, and then we can identify the tag, is it fake or real. So we create something called a confusion matrix, where we can actually compare the new unknown, let's say, new unknown emission excitation map to the stored data. And very clearly we can see among 226 junior comparison pairs, we got around 22.4 successfully accepted. So 2024 is showing this is real tags actually, and just only 2 were rejected, which means they are not real ones. So among imposter comparisons where we have a fake tags, so we create around 6,445 fake tags. We actually get 6,389 correctly identified as a non-matched because this is fake tags, and this means our model actually worked like 99% accuracy through the authentication process. So finally, we can use machine learning for machine attack. So okay, so we create a number of bits. We store these number of bits into the machine learning, and we also can authorize the system. So how about if we're trying to attack the system? So how about of making the opposite way? So if we give the system, for example, a number of bits, if we give the machine learning a number of bits, let's say n bits known. Okay, let's say half bits we're giving to the machine learning. Can the machine learning predict the other half or no? So this is one model. We actually testing 4 different models to trying to attack our system. And each time we give a number of n bits, and we actually trying the model to predict the next n plus bits. This is called partial key prediction. So where we would like to see how strong our key generation out of this feature. This is still in progress. So actually, we're still developing these 4 different models using machine learning to predict the key and see how strong our buff system. So in summary, we can just say like copper indium sulfide quantum dots is kind of good materials for extraction more feature, and this will actually give us a higher complexity. It is also, by the way, a lower toxicity material compared to cadmium-based quantum dots. The fingerprint exhibition is actually stable, reproducible, and repeatable. We can have a strong inter-sample uniqueness. We also introduce a novel AI-driven authorization framework based on the concept of physical identity discovery. And finally, we trying to create a machine learning attack by testing whether partial key information can predict unknown bits using different 4 machine learning models. So at the end, I have to highlight my team. So mostly some of colleagues are very expert on machine learning modeling, some of my PhD, and also I would like to highlight April for sure, EBSRC for funding for PhD student. Yeah, and thank you.